Hello everybody, today we are going to talk about the high pressure behavior and the phase transition of a natural borate kernite. So this is the timetable for this video. We will start with a brief introduction to the topic. It will follow a part on the material methods, the results, and at the end the discussion and some take-off messages. Kernite is one of the source of boron alongside with other borate minerals such as ulexite, borax and colemanite. As you can see, there are some mines of kernite, in particular the Kernite mine with an area of several square kilometers, in which the two most common ore minerals are borax and kernite. Borates are used in the industry to make ceramic materials and special glasses, and an ability of an isotope of boron, the boron 10, is to absorb a neutron. As you can see, a neutron beam can easily pass through a piece of paper, an aluminum or a lead plate, but is eventually stopped by concrete, especially if in the concrete there are some borates as aggregate. So because of that, researchers have investigated the possibility to use borates and also kernite ulexite to make special concretes and tiles to reinforce the wall and the roof of unconventional research facilities in which neutron beam is used to investigate matter. The crystal structure of kernite is made by triangular and tetrahedral boron-oxygen units that are linked together to form the framework of the structure. There are also some sodium cations and water molecules, in particular O8 and O11. Here you cannot see the hydrogen of the water molecules, but this was my choice because at high pressure the hydrogen is never detected because of the poor scattering barrier of hydrogen itself, and therefore I just prefer to sterilize the picture and remove all the hydrogen atoms altogether. At high temperature, we have a pretty clear picture of what happened to kernite. There is the dehydration of the structure at 350 Kelvin, followed by the amorphization of the structure, and then at 800 Kelvin, a new phase without any water molecules takes place. At high pressure, there are three phase transitions detected by Silva et al. 2018, occurring in 2.5, 7 and 11 gigapascal, but actually we don't know anything about the deformation mechanism of kernite. We don't know anything about the elastic parameter of kernite and its high pressure polymorphs, and actually we don't know the crystal structures of the polymorph of kernite. Therefore, we decided to make a single crystal X-ray experiment. So how to create high pressure and study a material at high pressure? Well, a very common device is the diamond double cell, and here you can see what a diamond double cell is. Basically, there are two diamonds, and between them there is a metal foil, a gasket with a little hole in the middle, and this creates a pressure chamber, a micrometrical pressure chamber. And in this chamber you put your sample, in our case kernite, alongside with the pressure carry-bands, for instance ruby, and the liquid that transmit the pressure. Basically, when the two diamonds are compressed one against the other, they deform the gasket that extrude inwards the pressure chamber, and this increases the pressure of the fluid, which compress in a hydrostatic way both the sample and the pressure carry-band. Then you hit the sample with an X-ray beam, you collect the diffraction pattern, and you solve the structure of your mineral, and you see how the structure evolves with pressure. So when you work at high pressure, it's always important to work with a nice beam with a high intensity and so on. We performed the experiment at the DAISY Peter-free synchrotron in Hamburg. The data correction were very fast, the data quality was extremely high, and here you can see an example of the reconstruction of the H0 L-star crystallographic plane. As you can see, the peaks are very sharp, the intensity was okay, and again, the data were extremely good. Unfortunately, at high pressure, we don't see the hydrogen, but this is an inconvenience of a high pressure study, and we cannot do anything about that. So in this slide you can see the evolution of the unit cell parameters versus pressure. And if you look at the graph at your right, which represents the evolution of the unit cell volume versus pressure, you will see that there are two first order phase transitions occurring at more or less 2 gigapascal and between 6.5 and 7.5 gigapascal. In both cases, there is a significant drop of the unit cell volume. Interestingly enough, we didn't detect anything that can resemble a phase transition at more or less 11 gigapascal, and in this case our study differs from the one of Silva et al. 2018, and we will discuss about that later. I want to point out that the elastic parameters, the bulk modulus, which is the reverse of the compressibility, as it is stated in thermodynamics, differs in the free polymorph of kernite, and in particular the kernite 2 polymorph has the higher bulk modulus. Okay, we will discuss about that when we will see what happened to the structure of kernite 2 when there is the kernite 1 to kernite 2 phase transition. So in this slide you can see the crystallographic plane H0 SR in both kernite 1, kernite 2 and kernite 3. As you can see in kernite 1 and kernite 2 the peaks are very sharp, stain sensitivity is okay, and therefore kernite 2 was refinable. At the bottom of the slide you can see one of the main deformation mechanisms in the kernite 1 to kernite 2 phase transition. As you can see, there is the anti-clockwise rotation of the sodium site Na1 alongside with also the migration of the water molecules O8 and O11. Overall, an important feature to understand in this kernite 1 to kernite 2 phase transition is the increase of the coordination number of the sodium cations, then from 5-ish or 6 increase to 7. So in this slide you can see the movement of the sodium cations and the water molecules, in particular the O7 water molecules. This picture is taken along the B crystallographic axis, and I want just to say that kernite 2 was solved with an R1 of 9% more or less on average, which is good enough. And there were some problems with the kernite 3 structure, as you can see from the reconstruction of the usual H0 L-star crystallographic plane. The peaks are very low in intensity, and you have to trust me, they were not very sharp, so we still got decent cell parameters to do the elastic calculation and so on, but the data were not good enough to solve the structure of kernite 3, unfortunately. To summarize, we saw that the tilting of the boron-oxygen units is the most convenient deformation mechanism occurring in kernite 1 and kernite 2. As you can see, the shortening of the distances between ambient pressure and 6.5 gigapascal is not a big deal. We saw only two phase transitions occurring between 1.6 and 2 gigapascal and between 6.5 and 7.5 gigapascal. We didn't saw the third phase transition occurring accordingly to Silva et al. 2018 at 11 gigapascal. Lastly, I want to thank all the co-authors of this study that has been recently published. Here you can see the drawing. I want to thank Daisy for the allocation of the beam time and the Giovani Cristallography Italiani for this first online congress. I think this is a very good idea and maybe could be the future in the upcoming years.